Hey, welcome back. In this video, we're going to tackle finding the slope of a polar curve. This isn't a really too complicated of a subject, but first and foremost, I want to say this. So we're given this function that's a radius in terms of theta, like always is set up for a polar curve. The first thing that you might think is that, well, what we could do is find dr d theta. So just take the derivative of this function with respect to the independent variable, which is what we did with normal Cartesian functions. But importantly here, if you think about these units, on top you have a radius, and on the bottom you have a change in radians. What this then would tell you, if you found dr d theta, what this would tell you is the change in radius per radian. And again, that might be super useful. For again, what this would tell you, dr d theta, it would tell you as you change your angle just a little bit, it's telling you the change in the radius. But if we want to find the slope, what we're looking to do is find this rise over the run. So we have to actually go back to our original thinking of the slope of a line being dy dx. And then what we're going to do is exactly the same treatment that we did with parametric equations, is in order to compute dy dx, what we're going to do is actually compute dy d theta and divide that by dx d theta. And we can easily verify that these are equal just by multiplying both the numerator and denominator here by d theta, right? So canceling out that d theta differential. And we've actually seen these before, but I'll show these again. If we want to find dy d theta and dx d theta, we're going to use these relationships between y and theta here. Again, knowing that the cosine function here and the r function are both functions in terms of theta. So we have to use this product rule. So for dy d theta right here, I'm differentiating this using the product rule. First differentiating the r to get dr d theta times sine. And then adding the derivative of sine is cosine, and then multiplied by the r. Down here in the denominator, doing exactly the same treatment with this, differentiating this using the product rule. I first get dr d theta. Cosine of theta, and then I get negative sine when I differentiate cosine. Oh, this is a theta, by the way, times r. So then there we have it. This is the formula for calculating the slope of a polar curve. Again, it's importantly here that even though we're in polar coordinates, we want to describe slope with this rise over the run conversation for what we said before. Dr d theta is a legitimate derivative that we might need and actually is used in this formula, as you can see appears here, but it would not find the slope. It would calculate the change in the radius per radian. All right, so then in this example, we're being asked to find the slope of the line tangent to r equals 5 sine of 2 theta at theta equals 3 pi over 4. What we're going to do is use this to find the slope of that tangent line at this point. In order to do this, what we just need is our theta values for the sine and cosine evaluation that we have in this formula right here. We have theta, but we do need to calculate the dr d theta and actually r. And so I'll do both of those real fast. So first and foremost, to find r at this theta value, what I'm simply going to do is plug in this theta into this expression. So I'll get r equals 5 sine of 2 theta, which is 2 times 3 pi over 4. This can be simplified to be 3 pi over 2, so I get 5 times the sine of 3 pi over 2. 3 pi over 2 is 270 degrees. The sine of that is -1, so this gives me a -5. So first and foremost, my r value in this expression, when I'm using this right here, this function or this formula to find the derivative, that's going to be a -5. Second thing I want to do is I want to find my dr d theta, which is simply just differentiating both sides of this expression with this equation with respect to theta. On this side, this 5 is just a constant, but the derivative sine is cosine. I'll also get a factor of 2 out because of the chain rule. So this actually will become 10 cosine of 2 theta. All right, so now I've found my R value is -5. My drd theta is 10 cosine of 2 theta. Now I can plug all of this into that formula. And so dy dx, which is the slope of the tangent line for this curve, drd theta is 10 cosine of 2 theta. So that's this right here, multiplied by the sine of theta. And then on the other side here, I get r times the cosine. So I'll just plug in that r here is -5 times the cosine of theta. All over, I get this 10 cosine of 2 theta again. Now we're multiplying it by cosine of theta. And then we have minus the sine theta r. So this r is -5, so I'll make this a +5, and then sine of theta. So then this again is my expression for any theta value for this function. This would output the slope, but we're specifically looking for theta at 3 pi over 4. So at theta equals 3 pi over 4, all we need to do is inject that into each part of this. What we get is dy dx equals 10 times the cosine of 2 times 3 pi over 4. Times the sine of 3 pi over 4 minus 5, cosine of 3 pi over 4 over 10, again cosine of 2 times 3 pi over 4. Now this is the cosine of 3 pi over 4. Minus 5 times the sine of 3 pi over 4. And again, all of this is right here's exactly this expression with theta equals 3 pi over 4 plugged in. Now I need to evaluate this. 3 pi over 4 is this. It's in the second quadrant. The x and y coordinates are negative √2 over 2, comma √2 over 2. This case right here, by the way, when I multiply these by 2, in the same way that I did from here to here, these are going to be the cosine of 3 pi over 2. And you can verify all this, but I'll write these out. So this is 10 times the cosine of 3 pi over 2. 3 pi over 2 is a straight down vertical at 270 degrees. The cosine is actually 0 for that, so that becomes 0. The sine of 3 pi over 2 would be, or 3 pi over 4, excuse me, would be √2 over 2, though that doesn't matter because that 0 is going to zero out this first factor right here. Here I get -5 times the cosine of 3 pi over 4, and that's -√2 over 2. Down here, I actually get this same 0, so it's not going to matter too much. This ends up being, because it's exactly the same expression right here, is 0, and then cosine of 3 pi over 4, well, that's just -√2 over 2, but again, that will be inconsequential because of the fact that this term and this term go to 0. -5 sine, oh wait, this shouldn't be negative. I'm sorry, I just caught this right here. I think I had said that. Oh, it is positive right there. All right, okay, positive. Sorry about that. Just realized I had that wrong. That is then 5 times the sine of 3 pi over 4, and the sine of 3 pi over 4 is √2 over 2. So then I just need to evaluate this. In this case, these terms go to 0 in both of these right here because of that factor of 0. These end up actually being exactly the same because this negative cancels that negative. So I get 5 times the square root of √2 over 2 divided by 5 times the square root of √2 over 2. They're both positive. When they cancel, they're the same. It means I get out just 1. So as a recap to this technique, when I'm going to find the slope of a line tangent to a polar curve, the first 2 things I'm going to do are identify the r value given this theta I have. So in this case, I have this value of -5. That's this radius value for this polar curve. Then I find this dr d theta, which again, you don't need to deeply think about it, but that is the change in radius per radian for this relationship right here. But what I then do is inject those into this bigger, slightly gnarly slope formula. Again, I'm finding dy dx, which is the rise over the run or the slope of a tangent line, by using this dy d theta and dx d theta. Plugging in the information I have, this is a carbon copy of that, just with the dr d theta and the r's replaced here for those values. Finally, plugging in my theta value and then hopefully not making any mistakes as we do all the calculations to get, in this case, the slope of the line tangent to this curve right here, which is a rose, by the way, with 4 petals. But at theta equals 3 pi over 4, the slope of that line is 1.